So we're continuing our conversation about the Strengths of Attraction Lab. We've been through analysis questions 1 through 4. So we're going to finish up 5 through 10. Actually, we've already done 10. But we'll finish up 5 through 10 in this part of the video. So question 5 asks us to compare propanol, butanol, octanol, and hexane. So what we're really looking at here, if you look at the formulas, so we want propanol, butanol, octanol, and then hexane. We're looking at something with 3 carbons, 4 carbons, 8 carbons, and 6 carbons. So you would think that the substance with 6 carbons would fit in between the 4 and the 8 carbon molecule. But if you notice, hexane with 6 carbons has a much lower boiling point than even propanol with the 3 carbons at 100. So why is that? Well, obviously, the number of carbons isn't the only thing that is important here. You're seeing that the OH has an impact as well. So if this were hexanol, we would expect to see something in between butanol and octanol. But we're not looking at hexanol, we're looking at just hexane. There is no OH. And so it makes sense that 6 carbons is not going to boil at a predicted temperature when there's carbons as well as an OH. So hexane is even lower than, if you notice, ethanol with only 2 carbons. So what this is saying is that, yes, the number of carbons helps increase the boiling point, but an OH is much stronger. So you're going to get a much bigger impact with an OH than you are with just the carbons and the hydrogens and the London forces that they can create. So that hydroxyl group is really having quite an impact on the attractions between those molecules. If we go on to take a look at question number 6, examine the solubility data, we've pretty much talked about this one already. So you've got things that are polar are going to have a lot of oxygens where you can get dipole-dipoles and hydrogen bonding occurring. If you have a molecule where the primary structure is the hydrocarbon part, then you don't have anything that is strongly polar, so you wind up having it not dissolve in water. So we pretty much talked about that idea already. Moving on to question number 7. This one too we've covered pretty extensively. Which has stronger intermolecular forces, solids or liquids? Well, our data supports the fact that all solids are going to be stronger than all liquids. The 2 solids have not melted yet. The liquids have already melted. So the 2 solids melt above room temperature. All of the liquids have already melted at room temperature. So that tells you that the IMFAs holding those solids together are much stronger than the IMFAs holding the liquids together. Moving on to question number 8. We are now looking at the various molecules that are solids. So cetyl alcohol is a solid at room temperature. Explain why. Cetyl alcohol is an alcohol. So why isn't a liquid like the rest of the liquids that we looked at, the rest of the alcohols? Well, cetyl alcohol has 16 carbons as opposed to just 8 for octanol. So obviously 16 carbons is enough to give this molecule so many London forces that they stay together for a long time, so you wind up with a solid. Note that the melting point is still pretty low, so it doesn't stay together for a long time, but it still keeps the alcohol together long enough to go above room temperature and be a solid. The next question, number 9, asks us to take a look at now citric acid, which is also a solid at room temperature. What can you conclude? Well, if you look at the structure, cetyl alcohol has only 1 OH, whereas citric acid has 4. There's 1 on the left and there's 3 on the right. Plus, this is a carboxylic acid. There are 3 carboxyl groups. So you have also the potential for dipole-dipole attractions. So with all of those oxygens around, it makes sense that the stronger dipole-dipole hydrogen bonding attractions are going to drive up that melting point much higher than the cetyl alcohol. So even though citric acid is a smaller molecule, fewer carbon atoms, there are a lot more oxygen atoms, which helps drive up that boiling or that melting point because of the strength of all of those dipole-dipoles and hydrogen bondings. That leads us to problem number 10, which is based upon your experimental data, rank the 10 organics. Well, we've done that already. We ranked it back on the sheet over here. So here's the ranking. What you want to do for 11 and 12, and I think it's a good idea, even if you weren't in class, I think it's a good idea to try and summarize the big ideas that we've been talking about. Number 11, discuss your predictions. So if you were in class when I asked you to do the predictions, compare what you did with the ranking that we actually found out to be true. Discuss kind of why you had misconceptions. Number 12 is the big one. Summarize your findings based upon the data in terms of molecular size, intermolecular attractions, melting point, boiling point, and solubility. So what I don't need you to do is talk about each molecule individually. What I want you to do is talk about solubility. How does the size of the molecule impact solubility? How does the presence of one or more hydroxyl groups or one or more ketone groups affect solubility? That's really what I want you to do. Talk in generalizations. Now, in order to drive your point home, it's always really good to include examples. So if you are talking about something and comparing octanol to hexane works well, please do that. You are trying to learn how to be very thorough, be very analytical in your explanations. No, you're not in a lower level class anymore. You're in an upper level honors class. So you want to make sure that your answers are much richer than they used to be. Simply saying yes or no isn't good enough anymore. Now, to do that, don't turn off the video because there's one other idea that I want you to include in that summary. And that is with branched hydrocarbons. So this is a little side branch. This is a little sidebar, but it's something that I think is important for you guys to also see. So if we were to compare 4 substances, so let's use things with the C5H12 formula, but let's look at different isomers. So we'll look at the straight chain pentane. Then let's look at the isomer with 1 branch. And then let's look at the isomer with 2 branches. Okay, so we've got 3 different isomers here. If we were to look up the melting points and the boiling points, now I'm just giving you a hypothetical, but if the boiling point of pentane were 60 degrees, the boiling point of this 1-branched isomer would be, something around 50. And then the boiling point of this 2-branched might be down near closer to 40. And again, these are not actual numbers, but this is just showing you the pattern. So let's talk about why. Why is the straight chain higher than as you start getting branches? So 2 ideas come into play there. Number 1, this straight chain has the ability to have more contact points. You can fit another pentane right along here and have a whole lot of opportunity for IMFAs to form. So you have many more contact point possibilities. With something like this, you've got something sticking up. You've got a point sticking up here. That diminishes the contact ability. So you may not be able to get contacts around these carbons because this one is protruding up. Even more so with this. You can have contact points here or maybe here or maybe here or maybe here, but you don't have a huge number of contact points between 2 individual molecules. So fewer contact points means there's fewer molecules to break apart or fewer contacts to break apart, which means less energy is required. The other thing that comes into play to an extent, and this you can see this in viscosity, The longer molecules can actually get tangled in amongst each other. Single bonded carbons are very flexible. These chains are very flexible. So you can see if I have a long chain of carbons, how they could get tangled like hair or string or something like that. And so if they're tangled, it's going to take more energy to break them apart as well. If I have branches, the tangling capability decreases. So that lowers the amount of energy needed to separate things. So once again, two ideas that come into play when you're looking at branches versus straight chains. You have more contact points in straight chain, and you have tangling possibilities in straight chains. Less tangling, less contact points, the more branches you get. So that's another idea that I want you to add to your summary, just to make sure that you put that in your head. The summary is something that really is going to help make sure you understand ideas. So whether you were here for the lab or not, I think it's a good idea that you write a summary up and let me take a look at it. It's good practice. Okay, so that's the second part of the Strengths of Attraction Lab. I hope that this was useful. We will let you write your summary now.